Welcome to another deep dive. Today we are diving into the world of medical AI research.
Yeah, it's a fast-moving field.
Fast-moving, and I think a lot of people listening probably feel overwhelmed by just the sheer number of breakthroughs and advances.
Yeah.
And just keeping up with it all.
And that's exactly what we're trying to do here, give you a clear picture of what's happening, what's really important right now.
Yeah, I mean, we've gone through, just a ton of papers for this deep dive. And, yeah, it runs the gamut.
Yeah.
Everything from AI that can detect the tiniest signs of cancer in tissue samples to the creation of massive new data sets.
Yeah, that's going to help us get even better AI models in the future.
Fuel the future of AI.
Yeah.
Okay. So let's unpack this, starting with, I guess, how AI is really becoming a vital tool in medical imaging for diagnosis. I mean, that's a big one, right?
Yeah, I mean, it's being used everywhere, all different parts of the body, all different imaging techniques. So let's start with this paper by Anders Blille, Nida Maliki, Zhao Ji, and it's a very long list of authors. It's a big team.
Big team.
And they're looking at prostate cancer diagnosis.
Okay. And their aim is to potentially reduce the need for something called IHC, which is immunohistochemical staining, which I think is something that's been around for a while, and it's really helpful. Pathologists use it to really distinguish between, is this cancer?
Right.
Is this not cancer?
Right, but it's a slow process.
It is a slow process.
Yeah.
And it can add cost.
Yeah.
So the question they asked is, can AI look at these H&E slides?
Right, the hematoxylin and eosin, the standard stain.
Oh, standard stain, yeah. And, accurately classify, particularly these difficult to interpret glands.
Yeah, those borderline cases.
Borderline cases.
Where it's not really clear.
And it's like, well, maybe we need IHC.
Right.
And the results were pretty good.
Right. Yeah. They had an area under the curve, or AUC, ranging from 0.951 all the way up to 0.993 in detecting cancer.
I mean, those are some pretty big numbers. I know those AUCs. That's a pretty good model.
Yeah, 1.0 would be perfect. So this is pretty close.
That's pretty close.
And the main thing is they were able to reduce the use of IHC staining. So there are 3 different cohorts of these kind of difficult cases, and it reduced IHC use by 44.4%, 42%, and 20.7% across those groups.
I mean, that's a significant reduction.
Yeah, and they didn't miss a single case. There were no false negatives.
Wow. That's huge.
Yeah.
I mean, especially in an area where you're dealing with cancer.
Right. So you definitely don't want to miss anything.
Absolutely. So that's pretty promising.
Yeah. It suggests that we can use AI as a first look, maybe to flag those cases that need IHC. And that's a huge resource savings, potentially.
Absolutely. Okay, so now let's shift gears. We were talking about the prostate. Let's talk about the brain. And this study by Ahmed Taha, Salah Ali, and Mohammed Darwish.
Yeah, so they're looking at brain tumors. So specifically glioma, meningioma, and pituitary tumors.
Okay. And they're looking at, I guess, can we use AI to really accurately diagnose these tumors?
Right. And differentiate them from normal brain tissue as well.
Okay. And I guess the gold standard here is MRI, magnetic resonance imaging.
Right.
But just like looking at those slides, it can take a long time to look at all of these images. There's potential for error.
Yeah.
You have to really be an expert.
Exactly.
So they use these YOLO models, YOLO V7 and YOLO V8. And I always think it's funny, YOLO stands for you only look once.
Yeah. It's a SUN acronym, but it's a very powerful model.
Very powerful model.
It's fast because it looks at the whole image at once as opposed to scanning across it.
Okay, and speed is important, right?
Speed is very important, yeah, especially in medical applications.
Absolutely.
And so they fine-tuned these models, which means they took a model that was trained on like a very general set of images and then specifically trained it on brain MRI images.
So they specialized.
Specialized it.
Yeah.
And the results were, they were really good. They got 99.49% accuracy with YOLO V7 and 99.56% accuracy with YOLO V8.
Wow. I mean, that's pretty much perfect.
It's pretty close to perfect.
Okay.
Yeah. And they were able to classify into 4 categories: no tumor, glioma, meningioma, or pituitary.
That's amazing. I mean, it really does make you think about, we were talking about earlier, all of these people who are training in these fields, radiology and pathology.
Right.
What is their role going to be in the future with AI being able to make these, extremely accurate diagnoses?
Yeah, it's definitely going to change the landscape.
Yeah, absolutely. Okay, so now let's move on to another area, chest X-ray interpretation. Praveen Shastri, and again, a very big team. And this is interesting because of the scale of the data that they're using.
Yeah, this is a huge data set. They used over 5 million chest x-rays from India, and they trained their model on that to identify, a huge number of pathologies, 75 different pathologies that you can see on a chest x-ray.
And they were using some pretty sophisticated AI techniques here.
Yeah, they use things like vision transformers, which are a newer type of deep learning model that's good at, seeing the relationships between different parts of an image. And then different types of UNet models, which are good at segmentation, meaning like pinpointing the exact location of abnormalities.
So really zeroing in.
Zeroing in.
Okay. And the performance, again, these are some impressive numbers.
Yeah, so they achieved up to 98% precision and over 95% recall for correctly identifying these pathologies. And for just the simple task of saying normal versus abnormal chest x-ray, the numbers were even higher. They had 99.8% precision, 99.6% recall, and 99.9% negative predictive value for normal versus abnormal.
That's crazy.
It's really, really accurate.
That is really accurate. But this is a model that was actually implemented in the real world.
Yeah. So this wasn't just something that was done in the lab.
Right.
They implemented it in 17 different healthcare systems in India, including diagnostic centers, big hospitals, government facilities.
Across the board.
Yeah. And since they implemented it, it's processed an average of 2,000 x-rays every single day.
Wow. That's real impact. That's not just a research paper.
Yeah, no, this is being used to actually help patients.
Absolutely. Okay, so moving from the lungs to the eyes, let's talk about glaucoma.
Okay.
And this paper by Yuzhu Zhu, Qilu, Shengshen, and again, a large team.
Yeah, so they were looking at using AI to analyze fundus images.
Fundus images?
Yeah, so that's like a picture of the back of your eye.
Okay.
To try and detect glaucoma early.
And glaucoma is a leading cause of blindness, right?
Yeah.
So, early detection is key here.
Really important, yeah.
But I imagine there's a lot of variation in those images.
Right.
Depending on what kind of camera they're using, even, the person's eye itself.
Yeah, exactly. And that can make it hard for AI.
Right. So how do they address this?
Well, so they created a system with what's called a self-adaptive attention window. So basically what that means is the AI learns to focus on the most important parts of the image.
Okay, so it's like it knows where to look.
Exactly.
Okay.
Specifically around the optic cup and the optic disc, which are the main areas that you would look at to diagnose glaucoma.
Gotcha.
And they also use what's called a multi-head attention mechanism to combine like these local features, like what it sees when it's zoomed in, with the overall context of the image.
So it's getting the full picture, but it's also understanding those key areas.
Exactly.
And that worked well.
Yeah, it worked really well. They found that it was more accurate and it was more robust to these variations that we see in real-world images.
So more reliable, basically.
More reliable, yeah.
Okay. So now let's talk about something that I think is particularly important, which is, we always hear about AI bias.
Yeah.
So this paper by Nusrat Muniya and Abdullah Al-Zubair Imran really dove into this in terms of skin disease diagnosis.
Right.
Where, depending on your skin color, the accuracy of the model might vary,
Mm-hmm.
which, that's a really big concern.
Huge concern.
Yeah.
So they developed this really cool system called Dermatology Diffusion Transformer, or DERMDIT.
Okay.
And it uses these vision language models to actually create synthetic images.
So it can create more data to train on.
Exactly. So it can create more examples of skin lesions on different scare types.
Okay.
And particularly underrepresented skin types.
So it's addressing that data imbalance issue.
Addressing the data imbalance, which is often the root of these biases.
Yeah. And then finally, in medical imaging, we have this paper by Chen-Hung Chen on automating eyelid measurements. And I was reading this and I was like, wow, I didn't even know that was something that you would need to automate.
Yeah. It seems very niche.
Very niche.
But it's important in oculoplastic diagnostics. So basically, if you're doing any kind of surgery on the eyelid, you need to get these very precise measurements of like how far the eyelid is from the pupil.
Okay, and that's all done manually now?
Yeah, so it's done manually with, rulers and calipers and things like that.
Gotcha.
And so what Chen-Hung Chen was trying to do is automate this using AI. He was looking at a model called DynOV2, which is a vision transformer model that was pre-trained using self-supervised learning.
Okay.
Which means it learns from the data itself without needing a lot of human labels.
So it's self-taught, basically.
Yeah, basically self-taught.
Okay.
And what's really cool about DyNovi-2 is that it worked really well even in what they call frozen conditions.
Frozen conditions, what does that mean?
So that means that you don't need to specifically fine-tune it on a bunch of eyelid images.
Gotcha.
So you can just take the model as is, and it already has a really good understanding of, shapes and sizes and things like that.
Just from its general training?
From its general training.
Okay.
And then he used a couple of techniques called focal loss and orthogonal regularization to improve the model even further.
And those help with?
So focal loss basically helps the model focus on the harder examples, like the ones that are harder to get right. And orthogonal regularization helps it learn more generalizable features. So it can look at new eyelid images and still get it right.
It's not overfitting to the data it was trained on.
Exactly. And he found that, with these techniques, he was able to get really good results for all these different eyelid measurements.
Okay, wow. I mean, that's another example of how this is not just staying in the lab. This is really coming into the real world and potentially, changing how patients are treated.
Absolutely.
Okay, so now let's move on to LLMs, large language models.
Yeah.
Which are also really changing the field of medicine.
Yeah. So this is where AI can actually start to interact with medical knowledge and even communicate with patients.
Yeah. And this paper by Duliu, Yinglong, Sophia Zhuoqi, Tian Tang, and Rong Yin, I thought was really interesting because it was looking at medical history taking.
Yeah.
And, they point out that, any doctor will tell you that one of the most important things is getting a good history from the patient.
Absolutely.
But it's also very time-consuming.
Very time-consuming.
So they were looking at LLMs, particularly in the field of obstetrics and gynecology.
All right.
And they were focusing on infertility.
Yeah.
Which I imagine, that would be a very, sensitive topic.
Sensitive and important to get all the details right.
Yeah. So they were looking at, could these LLMs actually have a conversation?
Right.
A simulated conversation.
Simulated, yeah.
And gather this information.
Yeah.
And they tested ChatGPT-4 and ChatGPT-4 Mini.
Right.
And they actually set up an AI system that could have this simulated conversation with, these simulated patients.
Right. And they used 70 real-world infertility cases to kind of base the system on. And it turned out that, both models were pretty promising, but the smaller model, the 4 Mini, was actually better at extracting the information and getting a complete history.
Oh, interesting. So smaller is sometimes better.
Sometimes better. It suggests that, for certain tasks, like this detailed information gathering, a smaller model might actually be more focused and more effective.
Okay.
But the standard ChatGPT-4 did a slightly better job of suggesting diagnoses.
Okay, interesting. So maybe each has its own strength
and weaknesses.
Yeah.
Yeah, and the authors point out that this is still early research.
Right.
We need to do more studies in real clinical settings with real patients. And we need more data, more diverse patient data.
And to train the models on. Yeah. But it's definitely a promising area.
That's very promising.
Yeah. Okay, now let's move on to another really interesting application of LLMs, which is helping people with dyslexia.
Yeah.
And this paper by Xihang Zhao, Shohong Carol Jiang, Bo Pang, Xiang Tang, and Pinjie He looked at this.
Right.
And, they point out that there are existing technologies out there to help people with dyslexia, but they have limitations. They might not be very good for quiet environment.
Right.
Or they can change the meaning of the text, which
right.
obviously that's not what you want.
Not what you want.
So they developed something called LARF, which stands for Let AI Read First. And this is a method where they're using LLMs to annotate text to make it more readable for people with dyslexia.
Right. And it doesn't change the meaning of the text.
Okay. And how, this is fascinating to me. Like, how does it annotate the text?
Well, they don't go into the details of the annotation in this paper.
Okay.
But the idea is that the LLM, it analyzes the text and it adds these, extra cues to help people decode the words more easily.
Right.
And they did a pretty big study with 150 people with dyslexia to see how well it worked.
Okay.
And it turned out that it significantly improved both reading performance and the overall reading experience.
That's amazing.
Yeah, and it was particularly helpful for people with more severe reading difficulties.
So the people who need it the most.
The people who need it the most.
Okay. So now let's move back to, I guess, the the core of medical reasoning.
Yeah.
And this paper by Zhongcheng Wu, Wenlong Deng, Xinguan Li, Xing Liu, and again, a very big team.
Big team.
And they're looking at this need to make AI more transparent.
Right. Explainable.
Explainable, yeah. Because, you can have an AI that gives you a diagnosis, but, particularly in medicine, you need to know, well, how did it arrive at that diagnosis?
Right. What was the thought process?
Yeah. And they created this data set called MedReason.
Yeah, they realized that there weren't good data sets for this, so they created one.
Yeah.
And they did this by using a medical knowledge graph, so basically a structured collection of medical knowledge.
Gotcha.
To create these question-answer pairs where the answers included a very detailed, step-by-step explanation of the reasoning process.
So it shows its work.
Shows its work. And they also had these, reasoning paths checked by medical experts.
So they're accurate, and they reflect how doctors actually think.
Exactly. So the MedReason dataset, it has over 32,000 of these question-answer pairs.
That's huge.
It's a lot of data, yeah. And it covers a wide range of medical topics.
And they use this to train LLMs.
Yeah, so they trained LLMs using this data set and found that the models became much better at solving medical problems. Their best performing model actually outperformed other state-of-the-art models on a standard benchmark.
Okay, so that's really promising, that this approach of, focusing on that transparent reasoning can really help improve the AI.
Yeah, absolutely. It's not just about the quantity of data, it's about the quality.
Yeah.
Okay, so moving on. There's a benchmark that was developed for evaluating LLMs in anesthesiology, which is a more specific field of medicine.
ANSBench.
ANSBench.
Yeah.
And it was developed by Xiangfeng, Wentao Jiang, Zhengmao Wang, and a team of researchers.
Okay. And they're really looking at how well these LLMs reason.
Reasoning in anesthesiology, yeah. So they point out that, we're using LLMs in all these areas of medicine, but we haven't really focused on these really specialized areas.
Right.
So that's what ANSBench was all about.
So how did they evaluate that? What did they look at?
Well, so ANSBench has these 3 levels of reasoning.
Okay.
So you have factual retrieval, so just basic knowledge.
Gotcha.
Then hybrid reasoning, where it has to combine different pieces of information.
Okay.
And then complex decision making.
Okay.
And it also has questions in multiple languages.
Wow.
So they looked at how different things affected performance, like the size of the model, whether they used chain of thought prompting. So that's where you kind of encourage the model to think step by step.
Gotcha.
They looked at whether it could transfer knowledge from one language to another. And they also looked at whether fine-tuning the model on anesthesiology-specific data made a difference.
Okay. And I imagine they found that all those things do make a difference.
Yeah, they found that the model characteristics and the training methods really impacted performance.
Yeah.
And they also looked at how things like prompting techniques and model compression techniques, so basically ways to make the model smaller and more efficient, how those affect performance.
Okay. And then another way to improve these models is test time scaling.
Right.
And that was in this paper by Sheki Huang, Zhongcheng Wu, Hui Liu, Qianfeng Tang, and Juyin Zhu.
Right.
So test time scaling, what is that?
Well, it's basically a way to improve the reasoning abilities of LLMs during inference.
So after it's already been trained?
After it's already been trained. It's like a little extra boost.
Okay.
And they found that it consistently improved medical reasoning performance. And it even allowed smaller fine-tuned models to perform comparably to much larger models.
Okay, so that's really good because, some of these models are huge.
They're very computationally expensive.
Yeah.
So, but they did find that there's kind of an optimal reasoning token budget.
What does that mean?
So basically there's an optimal amount of thinking that the model can do at test time.
Okay.
They found that around 4,000 tokens of reasoning was optimal.
Okay.
If you make it reason for longer, actually performance can decrease.
Interesting. So there was a sweet spot.
There's a sweet spot,
right.
Yeah. And they also found that having better medical knowledge was more important than just increasing reasoning depth.
So it needs that base knowledge to work from.
It needs that base knowledge.
Okay. And then finally, we have all this medical research out there.
Yeah.
Tons and tons of research papers.
Tons.
And this paper by Yoon-Soo Kim, Michael Ong, Daniel Rogalski, and their team looked at how can we use LLMs to extract this information from the literature.
Right.
And specifically, they were looking at 𝗂𝗃.
Yeah, immunohistochemistry.
Immunohistochemistry.
Which we talked about earlier.
Yeah, which we talked about earlier.
And they were interested in extracting IHC tumor profiles from PubMed abstracts.
Okay.
So basically, a lot of research papers, they'll mention the IHC profile of a tumor.
Right.
But it's all kind of buried in the text.
Buried in the text.
Yeah.
You have to go through and find it.
Yeah, it would take forever to manually do that.
Yeah. So they created this automated pipeline called IHC-LL minor.
Right.
Okay.
And it has two main steps.
Okay.
So first, it has to classify the abstract. Is this relevant to IHC and tumor profiles?
Okay.
And then if it is, then it has to extract the actual information.
Okay.
And their best performing model, they use something called GEMMA2, which is another LLM.
Okay.
And they achieved really high accuracy and F1 score.
So they were able to find the information they were looking for.
Yeah, and it actually outperformed GPT-4o.
Wow.
Which is impressive, and it was faster. Yeah. So they started with over 100,000 abstracts, and they were able to narrow it down to a much smaller set of relevant abstracts and accurately extract the IHC tumor profile information.
That's great. And then finally, in terms of LLMs, we have this paper by Anthony Yazdani, Ihor Stepanov, and Douglas Teodoro on this suite of models for recognizing different entities in biomedical text. So, like names of diseases or genes or things like that.
Yeah, so this is called Named Entity Recognition, or NER.
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 And this is a key part of NLP.
Yeah, natural language processing.
Yeah. But the problem in biomedicine is there's so much specialized vocabulary.
Right, and it's always changing.
Always changing.
New things are being discovered all the time.
Yeah.
So they developed this system called G-Line NAR Biomed.
Okay.
And it's different from traditional NAR systems because it doesn't rely on these predefined lists of entity types.
Okay.
So it can actually identify new entities that it hasn't seen before.
That's a huge advantage.
Huge advantage.
Yeah.
So how it works is it uses these natural language descriptions to kind of figure out what the entity is.
Okay. So it can understand the context.
It can understand the context, yeah.
And this is called zero-shot recognition.
Zero shot, yeah, because it hasn't seen any examples.
Okay.
And they found that their system outperformed other state-of-the-art models in both zero-shot and few-shot scenarios.
So really robust.
Really robust.
Okay. Yeah. Wow. I mean, it's amazing how LLMs are really, being used in all these different areas of medicine, from, interacting with patients to finding knowledge in research, even improving things like reading. Okay, so now let's shift gears.
Okay.
Let's talk about tools and frameworks that are being developed to actually use AI in medicine.
Right. So taking the models and making them useful.
Yeah, making them practical. And this paper by Zifeng Wang, Junie Gao, Benjamin Danek, and their team really stood out to me. They're looking at using AI to create consent forms for clinical trial.
Yeah, informed consent forms.
Informed consent forms.
Yeah.
And they created this system called InformGen.
Right.
And, they point out that these consent forms, they have to follow very strict guidelines.
Yeah, regulatory guidelines.
Regulatory guidelines. And they're often created manually, which is time-consuming.
Yeah.
And, there's potential for error.
Right, you can miss things.
Yeah.
So they wanted to see if AI could help with this process.
And so the InformGen, how does it work?
Well, it uses LLMs to analyze research documents.
Okay.
And then it generates the content of the consent form.
Okay.
But they kept humans in the loop. So humans would still review and approve the final document.
Okay. So it's not just, spitting out a form.
No, it's a collaboration.
Collaboration, yeah.
And they found that it worked really well. It achieved almost perfect compliance with core rules based on FDA guidelines. And it did much better than just like a vanilla GPT-4o model. Okay. And in a user study, they found that it achieved over 90% accuracy in the information that it presented. And importantly, it includes citations.
Okay. So you can trace back where the information is coming from.
Exactly.
So that really helps with accountability.
Accountability and accuracy.
Yeah.
Yeah.
Okay, now let's move on to another tool. This one is for creating Circos plots, which are those circular visualizations used in genomics.
Right.
And the tool is called IntelliCircos.
IntelliCircos.
And it was developed by Mingyang Gu, Jimin Zhu, Kepeng Wang, and their team.
Yeah.
And they point out that these Circos plots, while they're very useful for analyzing complex genomic data, they're really hard to create manually.
Yeah, it takes a lot of time and effort to design them.
And to get all the different elements and relationships right.
Right.
So they developed 𝗫𝗠 to kind of streamline this process.
Exactly. So they curated a large collection of these Circos plots from published papers.
Okay.
And then they used LLMs to kind of analyze this collection and identify common patterns in how the plots are designed. So now, if you want to create a Circos plot, you can use 𝗫𝗠, and it'll give you suggestions and references to help you design it.
So it's like an AI assistant.
Yeah.
For Circos plots.
For Circos plots.
And that's really great because, I mean, that could save researchers a ton of time.
Absolutely.
Okay, so now we have ScanR and 𝗍𝗏.
Okay.
And these are two tools for accelerating something called horizon scanning.
Horizon scanning, yeah.
And these were developed by Lena Schmidt, Ocean Sharma, Chris Marshall, and Sonia Garcia Gonzalez.